Today we'll be discussing logical instructions and comparison instructions. First, coming to the logical instructions. What is the purpose of logical instructions, or what for we are using logical instructions? To perform logical operations. So given with the source operands, the instructions whatever been supported in ARM, they are used for performing bitwise logical operations on the two source operands. This is the syntax for using logical instructions. We are going to specify the opcode. Followed by that, we are specifying the conditional attribute, then yes suffix. As you know that whatever we specify within flower brace, it is optional in the instruction. And these are the operands we are specifying in the logical instruction. So RD is the destination register, RN is source register 1, and N is the source register 2. It can be either source register 2, which is named as RM in general, or it may be an immediate data, or it can be the result of barrel shifter operation. So there is flexibility for the third operand, what we are specifying. So it can be either an immediate data, or it can be source register 2. In general, it is named as RM, or it can be the result of barrel shifter operation. Okay. So this is the destination operand. N, RD is the destination operand, and N is source operand 2. RN is source operand 1. And condition attribute is optional, and yes suffix is optional. After execution of logical instruction, if you want to affect the flags, then you'll be giving yes to the mnemonic. Okay, this is about the syntax of logical instruction. We'll specify the instruction, then condition attribute, then yes suffix, and we'll specify the operands. First operand is the destination operand. Next operand what we specify is source operand 1. The third operand is source operand 2. Okay. So this is about the syntax. Coming to the logical instructions supported in ARM. So these are the 4 logical instructions supported. That is AND instruction, OR instruction, EOR instruction, and BIC instruction. We already discussed these 3 instructions in the lab programs. That is AND, which stands for logical bitwise AND of two 32-bit values. ORR, it is for logical bitwise OR operation of two 32-bit values. EOR, it is logical exclusive OR of two 32-bit values. And the last instruction is BIC, which stands for bit clear. BIC mnemonic stands for logical bit clear. And you can see the last column in the table. What is the operation performed by each of these mnemonics? You can see RD equal. In the previous slide, you saw the general syntax, right? This is the general syntax you have seen. RD, RN, M. And what is the operation performed? With this syntax, the table is explained here. In the last column, the operation is specified. This, that is the source operand 1 is ANDed with source operand 2. Whatever the result you will get, that will be stored in the destination register. And you know the truth table of AND, right? The same truth table holds here. Similarly, OR instruction, the source operand 1 is ORed with source operand 2. The result is stored in destination operand. EOR instruction, it is exclusive OR operation. Source operand 1 and source operand 2 are XORed. The result is stored in the destination register. So these 3 instructions you are already aware of. The last instruction is bit clear, logical bit clear. What this instruction will do is, it takes the ones complement. That means it inverts the second operand and it performs the AND operation with the first operand, that is the source operand 1, and the result is stored in the destination register. Hope I'm not confusing you. What is the syntax of logical instruction? The opcode, then we'll specify RD, the destination register, then we'll specify RN and N. This is the order in which we are specifying the operands. What bit clear instruction will do is, it takes source operand 2, it inverts the bits in the source operand 2, and it performs AND operation with source operand 1, that is RN, and the result is stored in destination register. Hope this is clear. Okay, so this is about bit clear instruction. So these are the instructions supported in logical instructions category. So what are the important points you need to remember with respect to logical instructions? So the first point is, with respect to bit clear, what is the application of bit clear instruction is? So this instruction is useful when clearing status bits, and it is frequently used to change interrupt mask bits in CPSR. So if you want to change the status, say for example, if the bit status is 1 and you want to mask it, so in that case you can just make use of BIC instruction. Usually it is used in changing the interrupt mask bit status in the CPSR register. So once we go to the program status register instructions, the instructions in that category, how actually bit clear instruction can be used to mask the intra or to enable the interrupt mask bits. So that we'll discuss with an example. Okay, for the time being, just know that bit clear instruction is useful for clearing the status bits, and it is frequently used for changing the interrupt mask in CPSR register. And you already know the flags which are affected once logical instructions are executed, and only when the logical instructions will affect the flags. So if you are giving yes suffix in the instruction, then only it is going to affect the flag. Okay, which flags are affected? You know, move instruction and logical instructions, they are going to affect negative flag, zero flag, and carry flag. So only if this is possible, only if yes suffix is present in the instruction, and overflow flag is unaffected. So in move in and logical instruction, overflow flag is not at all affected. Before execution of the instruction, whatever was the status, the same status will be retained after execution of the instruction. So the only flags that gets affected are N, Z, and C. So this is possible only if yes suffix is given in the instruction. So such problems where yes suffix may be given or may not be given. So if an instruction set is given, if they ask you to find the result after operation and status of the flags, this is the common question you can expect. Carefully you have to analyze the instruction, and you have to first think what flags will be affected once that particular instruction is executed, whether yes suffix is given or not. Everything you have to check, analyze, and then only you have to decide about the output. Okay, so this is about the flags that will be affected. And similar to arithmetic instruction, the second operand, source operand, what you will specify, it can use barrel shifted, that is the result of barrel shifter operation can be specified as n. Okay, so these are the points you need to remember with respect to logical instructions. So what are the important points you need to remember with respect to logical instructions? They are used for performing bitwise logical operations, and the four logical instructions supported are AND, OR, ORR, EOR, and BIC. AND is meant for performing logical bitwise AND operation, OR is for logical bitwise OR, EOR for logical exclusive OR, BIC, what this instruction will do is it takes the second source operand, it inverts the bits, and it performs AND operation with source operand 1, and the result is stored in destination register. So these instructions are going to affect N, Z, and C flags only if yes suffix is given in the instruction. V flag is unaffected. Okay, and the application of bit clear instruction for changing the interrupt mask in CPSR will be using bit clear. Okay, coming to few problems on logical instruction. Just one example I am giving here. Uh, Perform logical AND operation between R1 and R2 and store the result in R0 register. If this is the precondition, say R0, R1 and R2, and if this is the flag status, if I want to affect the flags after execution, I need to give yes suffix. See, as given in the question, it is AND operation to be performed. So the mnemonic we have used is AND, and we have given yes suffix to the instruction. This is the order of the operands we have given. As per the question, R0 is the destination register. You need to perform AND operation between R1 and R2. This is the instruction you can write. AND S R0, R1, R2. Once this instruction is executed, what happens? It takes R1 content and R2 content. It performs AND operation between these two. So just have the binary representation of these two data, 32-bit data, and apply the truth table of AND operation. If the corresponding bit, what you are comparing, if any one bit is 0, resultant bit will be 0. So that will be the AND operation result. Here R1 and R2 are the source registers which are unaffected. After performing AND operation, this is the result you are going to get in R0 register. You can verify the result, okay, later. R1 It is unaffected. It is having the same data whatever we had in before execution, and similarly R2 register. Now, what about the flags? So is it going to affect any of the flags? Since we have given yes suffix, as you know that logical instruction will affect N, Z and C flags. So C flag is not at all affected since we are not using any barrel shifter operation here. That's why C flag is not affected. And Z flag, just see R not register, its content is not 0. That's why 0 flag status will be 0. And see the most significant bit in R not register, it is 0 here. That's why negative flag will also be 0. So whatever the status we had before execution, same flag status you will see after execution. So if this has resulted with MSB as 1, in that case negative flag would have been set. Only when carry flag will be set in logical instruction is when you use barrel shifter operation. You are performing logical shift left or logical shift right, and that result you are using for performing AND operation. During that case, when whatever the data left shifted or right shifted, that status will be appearing in the carry flag. Otherwise, the carry flag is not affected in this normal AND instruction. Only if the second operand what you specify. Say for R2 register, if I use barrel shifter operation, and if say for example, if I am performing right shift operation and least significant bit status was 1, in that case carry flag would have been set. Okay, so this is about simple logical AND operation. Coming to the next problem, which is a bit interesting. See, clear bits at odd positions without affecting bits at even positions in R2 register and store the result in R0 register. So what is the operation you are performing? This already we have executed in the lab. Which instruction you have used to clear the bits at odd position without affecting bits at even position?
And operation.
And operation, right? You have already used and operation, where what is the amount shift? The mask amount you are taking to perform and operation. Odd position bits are to be cleared. Tell me the 32-bit mask value you are going to consider. So start from least significant bit. Just think of the nibble, lower nibble, then you'll get what should be the data in complete 32-bit.
101010.
1010 I'll take. You should not mask even bit data, odd position bits.
0101.
0101 means what is that value? Hex value. 0101 constitutes what hex digit?
10 corresponding A.
No, 0101.
5, ma'am.
5, right? Forgotten the binary representation of 5. 0101, it is 5. Okay, 8 hexadecimal 5s you are taking and you are performing AND operation. So that will result in that is clearing of data at odd position without affecting data at the even position. So this is one way of implementing. What we are going to see now is, in addition to that, how actually we can make use of bit clear instruction to clear these bits at odd position. So how to make use is, whichever bit you want to clear, that bit status you take it as 1. Rest other bits which you don't want to affect, take its bit status as 0. What bit clear instruction will do? Can anyone explain what bit clear instruction will do? Yes? What is the use of bit clear, or what is the operation performed by bit clear? Just now I explained. Can anyone quickly tell what operation is performed?
It will invert the second operand and
Ah,
performs bitwise AND.
very good. Okay, so now the mask value what you are going to take, it should not be 5 here as you are doing for AND instruction. Since bit clear, it first inverts the bits and then that data will be taken for performing AND operation. So how to make use of bit clear instruction for such problems is, whichever bit you want to clear, so that bit status you take it as 1, so that once it is inverted, its value will become 0. So whichever bit you don't want to affect, take its status as 0. So once inverted, it becomes 1. And once you perform AND operation with that, whatever the problem you wanted to or that solution what you are expecting, you are going to get. See how we are doing it. R0 is loaded with 0, and R1 register which holds the mask value, it is not 8 5s, it is A. Why we are taking A is what it indicates. Just see the binary representation of 8 A's. What you are finding is in odd positions we have taken 1 as the bit status. In even positions we have taken the bit status as 0. And now we'll perform, and this is the data I have considered, which is as taken as an input here. In this data, I need to mask only the odd position bits. So this is the bit clear instruction we are executing. BIC R0, R2, R1, where R1 holds the mask value, R2 holds the input data, and R0 is the destination register. So what is the operation performed? It takes R1 register content, source operand 2, it inverts the bits. So all 8 A's inverted means what will be the value? What will be the result? If you invert
all
10,
All fives.
all fives, right? That is same as directly taking fives, 8 fives and performing AND operation. So here it inverts, so it will be all 8 fives. That will be considered for AND operation with R2 register, and the result of AND will be stored in the R0 register. This is what bit clear will do. So how to make use of bit clear in this? Whichever bit you want to clear, take that bit status as 1, not 0. Since first it inverts and then it performs AND operation. So this concept you need to understand. See, post condition will be R2, R1 are source registers. They are not affected. R0 is having the value 5. R1 is having A and R2 is having all Fs. So since they are source registers, they are not affected. Only R0 is having the result of bit clear operation. So, and another implementation, as you told, say R1 is having the mask value. I can make use of AND instruction directly, and R0, R2, R1. So the result will be the same. So once you see R0 register, it will be having all fives. Okay. So this will be the result. So that's what I have shown here. See, this is the input I have taken, all 1. That is 8 Fs I had taken as input in R2 register. And to make use of bit clear instruction in odd positions, you can observe, start from least significant bit. B0 bit status is 0, I have taken. B1 bit is 1, B2 is 0, B3 is 1, and so on. So here, whichever bit I want to clear, I have taken it as 1. Unaffected bit status will be 0. Once you perform bit clear operation, what it does is it inverts the bits. The second operand what we have taken, all A's, they get inverted to all 5's here. So this data is taken to perform AND operation with, that is 8 F's. So what will be the result? It will be, that is all 5's. That will be the result. So since 1 ANDed with 0 will be 0, 1 ANDed with 1 will be 1, 1 ANDed with 0 will be 0, again 1 AND with 1 means it is 1. So all 8 5's you are going to get as the result in R0 register. Okay. Coming to the next problem, you need to perform exclusive OR operation on the two operands. Perform A exclusive OR B. Here we shall assume R1 contains the value of A and R2 contains the value of B. And you know the formula, the logical formula for computing exclusive OR. A exclusive OR can be written as, the expression can be A complement ANDed with B, or A complement, A ANDed with B complement. So if you know this, you can go for different ways of implementing the same problem. So what is a direct way of implementing this problem? Performing exclusive OR between A and B. What is the solution? What is the simple solution?
EOR of R1, R2.
R2, simple. So if you don't want to affect R1 register, so you can take the third register, EOR R3, R1, R2. You know, in R, EOR instruction is supported, which performs exclusive OR operation. So we are performing exclusive OR operation between R1 and R2. The result is stored in R3 register. This is the direct implementation. If it is specified in the question, not to use exclusive OR operation and to perform the same operation. You need to get the result of exclusive OR operation between A and B, but you should not make use of EOR instruction. Then how to implement? So what is the other way of implementing? You can
clear
see
at
this formula.
bit clear.
Yes, you can make use of bit clear, or you can make use of MVN instruction for inverting the bit. How to find the complement of the operand? I can make use of MVN instruction, right? See, another way of implementing is, first what I'll do is I'll take the complement of A. R1 register holds A value. I'll take its complement using MVN instruction, that I'll store it in R3 register. So now what I'll do is I'll perform AND operation between R2 and R3. So I got the value for A complement B. Hope you are getting MVN R3 R1 and R3 R2. Next, similarly, I will perform operation between that is the second term, that is A ANDed with B complement. Assume in R2, you are having B value. So tell me the MVN instruction. Say R4 is a register which holds the complement of B. Assume R4 holds complement of B. Tell me the MVN instruction to get the second term. Yes.
MVN R5, R4.
R2 is the register which holds B value. Just see the question. R2 is the register which holds
MVN
B.
R4, R2.
R2. Okay. MVN R4, R2. It gives the complement of B. Now I need to perform AND operation with A. What is the statement or the instruction? R4 is having complemented value of B.
And R4, R1.
R1 and R4, R1. What is the final operation I have to perform? See, in R3, I am having the first term value. In R4, I am having the second term value. I need to perform OR operation between these two. So, ORR is the mnemonic. You can perform ORR R3, R4. See, this is another way of implementing. If they ask you to implement using that is MVN instruction, this is how you can perform the operation. If nothing is specified, it is left to you. Whatever the instruction you want to choose, using that you can implement. If they explicitly give that without using this instruction you have to implement, or using this instruction only you have to implement, in that case, carefully you have to find the solution. Okay. So as you told, bit clear instruction can also be used. For bit clear instruction, what it does, it first inverts and then it performs AND operation. So directly I can perform, I can calculate each of this term with a single instruction. See how to do? Bit clear R3, R2, R1. See what it will do? It inverts R1. It takes the complement of R1 and it performs AND operation with R2. It stores the result in R3. So second instruction, what can be the second instruction to compute the second term? We are performing bit clear R4, R1, R2, where R2 is having B value, B is inverted, it is ANDed with A value, and then the result is stored in R4. The last instruction is OR operation. I can perform OR R3, R4. Are you getting? See how we have used bit clear instruction to implement this? In the first solution, what you are seeing is separately we are complementing and then we are ANDing to compute each of the term. Whereas in second solution, each term is calculated or computed using one instruction, BIC, inverted and ANDed. Similarly, second term we have computed like this. Second operand is inverted, it is ANDed. The results are in R3 and R4. They are OR finally. If you check the results when you implement and execute, if you just compare the results in each of these different logics, you'll get the same result. Have you all followed how to perform exclusive OR using MVN, BIC and EOR? Clear? Yes or no?
Yes, ma'am.
Okay, so this completes logical instructions. Such interesting problems you can expect, so kindly be thorough with the instruction set. Okay. Coming to the next category of instruction, that is comparison. And remember, all these are under the category of data processing instructions. So far, under data processing instructions, we have covered move instructions, arithmetic instructions, logical instructions. We are left with comparison instructions and multiplication instructions. If we complete comparison and multiplication instructions, that will complete data processing instructions category. Then we'll be discussing branch instructions, load store instructions, program status register instructions, and software interrupt instructions. So for your internals, it is still branch instructions. So after comparison, two more category of instructions are left out. That is multiply instruction and branch instructions. Okay. Coming to the comparison instruction, this is the purpose of using compare instructions. They are used to compare or test a register with a 32-bit value. What do you mean by testing a register with 32-bit value? What instructions are supported? We'll see in the table in the coming slide. So just know that whenever you are having two 32-bit data, if you want to compare the values of that, then you can make use of compare instruction. Or if you want to test a particular bit in the instruction, you can make use of this comparison instruction. And these comparison instructions, they are meant for affecting the flags. This is one more important point you need to remember. Comparison instructions, if you see the syntax in the next slide, you can observe that yes suffix is not given in the syntax. That means if you simply use comparison instructions, they are going to affect the flags and they are not going to affect the operands what you have specified in the instruction. Remember, whatever the instructions we have discussed so far, uh, destination operand was getting affected once the operation is performed, whereas this is an exceptional instruction category where it is going to affect the flags based on the result, but none of the operands will be affected in comparison instruction. Kindly remember this. What is the purpose of comparison instruction? They are used to compare or test the register with 32-bit value. They are going to update the CPSR flag bits according to the result, but they are not going to affect the registers used in the instruction. And yes suffix should not be given for the comparison instructions. In else, assembler will raise an error if you try to give yes suffix to the comparison instructions. So in the syntax, it is clearly mentioned that you are not supposed to use yes suffix since these instructions are meant for affecting the flags. So it performs internally the specified operation, but based on the result, the flags will be affected. None of the registers specified in the instruction will be affected. And you can use the status of the flags after performing comparison operation. You can use the flag status to perform the control transfer. The program flow can be controlled by using conditional execution instructions. That's what I mentioned here. Coming to the syntax of comparison instruction. See, instruction, the opcode will specify, then the condition attribute. You can give the condition attribute rn comma n. You can observe yes suffix is missing here. You should not give yes suffix to the comparison instruction. So what is rn? And you are not seeing rd register in the general syntax, as you know that this instruction is not going to affect any of the operands. Result will not be stored anywhere. It performs the operation and it affects the flags based on the result computed. Result will not be stored. Okay. So here Rn is source register 1 and N, as you know that it can be either an immediate data, source register 2, in general it can be called as Rn, or it can be the result of barrel shifter operation. So what are the comparison instructions supported in R? Okay. These are the 4 comparison instructions supported: CMN, CMP, TEQ, TST. Already we have used CMP and TST instructions in the lab practice programs. Anyway, we shall discuss all these 4 instructions once again. See, coming to CMN instruction, it stands for compare negated. CMP stands for compare. TEQ stands for test for equality of two 32-bit values. TST stands for test bits of 32-bit value. How to make use of these instructions in the program, that we'll see with examples. Okay. And what is the operation performed internally? That is given in the third column of this table. CMN instruction, what it does is Internally, it performs addition operation of the two operands specified, and then based on the result, it is going to affect the flags. Okay. Then what is the equivalent instruction to CMN? CMN instruction will perform addition and it affects the flag. Can anyone tell the equivalent
Add
instruction?
S.
Add, yes, very good. Add S instruction is equivalent to CMN instruction, but what is the only difference between CMN and add? Add S? What is the only difference?
CMN will not store value anywhere.
Yes, very good. This is the difference you have to note. Add instruction after performing addition. Result of addition will be stored in the destination register. Whereas in CMN instructions, it performs the addition of the two operands. Based on the result, it affects the flag, but it is not going to store the result in any of the register specified in the instruction. This is what you need to know. So next, CMP instruction. What is the equivalent instruction for compare? Compare internally, what is the operation it performs?
Sub-S.
SUBS.
Yes, very good. SUBS. Okay, internally it performs subtraction and it affects the flags based on the result, but it is not going to store the result. Result will be discarded when compare instruction is executed. Based on the result, only flags will be affected. This is about compare instruction. TEQ instruction, it performs exclusive OR operation between the operands. Then what is the equivalent instruction for TEQ? It will not affect the registers TEQ, but only it performs the exclusive OR on the operands. What is the instruction? Logical instruction supported to perform exclusive OR? Tell me the mnemonic after execution of which it affects the flags. Which is the instruction?
EOR
EOR.
yes, RN,
EOR,
N.
yes, yes. You need to give EOR, yes. The equivalent instruction for TEQ is EORS. That is the logical instruction. This is the comparison instruction supported. It performs exclusive OR operation between the operands, and based on the result, it affects the flag, and the result will be discarded. TST instruction, just see the last column, last cell. The flags will be set as a result of Rn and N. That means it performs AND operation between the two operands and it affects the flags. Result will be discarded. So TST instruction is equivalent to which logical instruction?
And S.
And S. Very good. See, now we shall just recall. CMN instruction is equivalent to add S instruction. CMP instruction is equivalent to SUBS instruction. TEQ is equivalent to EORS instruction. And TST is equivalent to ANDS instruction. But in this comparison instruction, result will be discarded. Only flags will be affected. And you should never give S suffix in these four instructions. Kindly note these points. Okay. Coming to the important points to be remembered. So CMP, CMN instruction, they are going to affect all the flags. Why they are going to affect all the four condition flags? You know, in arithmetic instructions, they are going to affect all the four flags. Since CMP internally performs subtraction operation and CMN performs addition operation, they are going to affect all the four condition flags. Whereas the other two, TST and TEQ, can anyone guess which flags will be affected when TST and TEQ instructions are executed? Recall the equivalent instruction for those two. TEQ and TST. Which flags will be affected?
Z flag.
Only Z. Logical instructions and move instructions are going to affect negative flag, zero flag, and carry flag, right? Since TST will perform internally AND operation, TEQ will perform OR of exclusive OR operation. They are going to affect N, Z, and C flags. Remember this. CMP, if you know the equivalent instruction, you can remember the flags that will be affected. Okay, CMP and CMN will affect these four flags. TEQ and TST will affect only these three flags. And you are not going to give S suffix for the comparison instructions. Okay, and this we
Ma'am,
already discussed. Yes?
ma'am, how will it affect the C flag?
Barrel shifter. You saw the general syntax, right? Result of barrel shifter operation, N. If I give LSL, logical shift left, if I take the value 1, okay, huh? If I take the
Yes.
value 1,
Yes.
if I perform logical left shift, n can be, see what is the explanation given in the syntax? It can be an immediate data or source register m. So if I write the instruction as, say in this, which instruction you want? TEQ or TST? Okay, if you want TST, if I write TST R3, R1, R2, LSL hash 1, if you write, if the data what you have taken in RM register, it is having the that is the most significant bit as 1. When you perform logical shift left, the carry flag will be set. If your LSB bit is 1 and if you are performing logical shift right, then it is going to affect the carry flag. That means its carry flag bit status will be 1. Are you getting? Result of the status of MSB and LSB will be saved in the carry flag if these instructions are executed with barrel shifter operation. The carry flag will be affected only if you are using barrel shifter operation in the instruction. Am I clear? Okay. With respect to TEQ and TST, I am telling. TEQ and TST. Whenever you are using compare and
Yes,
CMN,
ma'am.
when carry flag will be affected, you all know. Can anyone tell when carry flag will be affected when CMN instruction is executed? CMN, when carry flag will be affected? CMN internally what operation it performs?
And borrow is
Ma'am, borrow. It'll.
CMN internally what operation it performs? What is the equivalent
addition.
instruction for CMN? Addition,
Add.
right? Borrow, why borrow will come when you add? What you should tell?
If carry
When
is generated, then it will.
out of MSB, okay? When carry out of MSB is there, then only carry flag will be set with respect to CMN. What about CMP? Internally, what operation it performs? It is subtraction operation,
Subtraction.
right? And exceptional case with respect to subtraction. Kindly recall that exceptional case. If borrow is generated into MSB, what will be the status of carry flag?
It will be 0.
0. If borrow is not generated, carry flag status will be 1. This is with respect to CMP instruction. So if you consider TEQ and TST, these are actually internally they are going to perform logical instructions. When carry flag will be affected is if you are using for the second operand barrel shifter operation, then only it is going to affect carry flag. Otherwise, based on the result of operation, either N or Z flag will be affected. Am I clear? Hope you are getting. If the result after performing say AND op, you have used TST instruction, you are performing internally AND operation. If it results in value 0, Z flag will be 1. After performing AND operation, if you find that the most significant bit of the result is 1, N flag will be set to 1. So this is how TEQ and TST will affect the flags. Carry flag, it will be affected only if you use barrel shifter operation in these instructions. That is TEQ and TST. Okay. And rest other, as I've already discussed, CMP is a subtraction instruction SUBS with result discarded. CMN is an addition instruction ADDS with result discarded. TST is a logical instruction ANDS with result discarded. And TEQ is again a logical instruction EORS with result discarded. So this is what the important note you need to remember with respect to comparison instructions. Now we shall see a few problems on comparison instruction. So already we have seen different logics for finding the solution for this problem. I've considered the same problem here. Check whether the number in R0 register is positive or negative. If positive, then store 10H in R2, otherwise store 20H in R2. This we have implemented using barrel shifter in the move instruction. We have used RRX instruction and we have implemented. Another way is we can make a comparison instruction and we can implement it. Which comparison instruction I can use to test whether the given number is positive or negative? Can anyone tell the out of the 4 comparison instructions CMP, CMN, TST and TEQ, which instruction I can use to implement this problem? Which bit I need to check whether it is to infer whether the number is positive or negative, which is the bit I have to MSB, right? We are having test instruction TST performing AND operation with 8 followed by 70, what it results in if the MSB bit is 0. That means if you have taken a positive number, for that number, if you perform AND operation with 8 followed by 7 zeros, what will be the result? Are you getting? If this is the data I am taking, 8 followed by 7 zeros. Okay. If this is the value I am using to perform test operation, what will be the result if you have taken a positive number? Hope you are getting the question. If
Result
you taken the,
zero.
Zero,
what will
zero.
be the result of
8
AND?
Zero, ma'am.
8 7
Zero, ma'am.
Positive.
If you have taken positive, I'll take 2 as the input. 2 is a positive number, right? If I take 2, it is hexadecimal data, what I have shown here. If this is the value I have taken to perform, that is test instruction. If this is the input I have considered, that is 2. When you perform AND operation between these two, what it results in?
Zero.
8 means
Zero.
1, 0. Result will be 0. If it results in 0, what you can infer? The number is positive or negative?
Positive, ma'am. Positive number.
Positive. So if you have taken, say, f followed by all zeros here, and say it may be all zeros or 2, it doesn't matter. Just concentrate on the MSB bit. If it is f and you are performing AND operation, f means it is 1111. The most significant hex digit only I am showing here, and 8 means it is 1000. This is the data. When you perform AND operation between this data, if the MSB bit is 1, it results in 1, rest other bits will be 0. That means it results in a non-zero value, right? So this is the value we are taking, mask value we are taking to perform test instruction. So whichever bit you want to test, that is whether it is 1 or 0, you can take only that bit status as 1, and rest other bit status you can take it as 0. Are you getting? See how I have done it? Assume R0 is having this value, the input, and R1 I have taken it as 8 followed by 70, since I need to test the MSB bit. If the MSB bit were to be 0, the result of test operation will be 0. TST R0, R1. So if this will result in value 0 if it were to be positive number. But in our case, it is a negative number we have taken where MSB bit is 1. R0 is the register which is holding the input. So now see, then what I'll use is, I'll use the conditional attribute move EQ. So that means if Z flag status is 1, then we can interpret the number is positive. Whatever the number held in R0 register is positive. So that's why, as per the question, we are going to store 10H in R2 register. Otherwise, we are going to store, if it were to be 0, then we are, that is, if the result is non-zero, where 0 flag status is 0, in that case, we are going to store 20H in R2 register. Are you getting how actually it performs the test operation? So this is the data we have taken, F3425618, and we are performing AND operation with 8 followed by 7 zeros. What it results is in a non-zero value. If it results in a non-zero value, what we can infer is the MSB bit is 1. If it results in a 0 value, then we can infer that MSB bit is 0. That means the number is positive. Simple. Clear? That's how we can make use of test instruction. Now, can you tell how to make use of the same test instruction to check whether the given number is odd or even? What is the mask amount I need to consider? Which bit I have to test to check whether it is odd or even? This logic you have used in one of the practice question.
Ma'am, LS, you have to consider register 1, ma'am.
Yes, LSB, right? What is the mask value I need to take? With what
1.
value I need to perform AND operation with the
1.
input? 1, right? For MSB bit, to test MSB bit, just see we have used 8 followed by 70. MSB bit only we have taken as 1, rest other bits as 0. So to check whether it is odd or even, we are going to take the LSB bit as 1 and rest other bits as zeros, and we'll perform the AND operation. If LSB bit is 1, then performing AND with 1 will result in non-zero value. With this we can infer that it is an odd number. If the least significant bit were to be 0, performing AND operation with 1 will result in 0, from which we can infer that the number is, that is even. Okay. See, assume R0 is having the value 10H. It is 16 in decimal. You can see least significant bit is 0 here. TST R0 comma hash 1. Just observe the test, the mask value what I have taken. Once you perform AND operation with 1, it is going to make the 0 flag status as 1. Result of operation, this AND operation is 0, which affects the 0 flag. With that, we can infer that the number what you have taken is even number. Are you getting? See, move EQ R2 comma EQ means if Z flag status is 1. Just see the same example what we have taken. R0 is having 10H. We are performing test R0 comma hash 1. So 10H means what is the value? Let me write here if you are not following. 1 means it is 0001, correct? 10, this is 1, 0. I'm not showing complete 32-bit data. Let us see for only 8-bit. And we are performing AND operation with 1. 0, 0, 0, 0. Okay. 0, 0, 0, 1. This is the data I have taken. I have taken 16 in decimal. This is 16 in decimal. To check whether 16 is odd or even, I am testing only the least significant bit. Test instruction I am using to test only the LSB bit. So to infer whether the number is odd or even, if I check only the LSB bit, that is sufficient. If the LSB bit is 1, we can infer that it is an odd number. If LSB bit is 0, you can infer that it is an even number. How to test it using test instruction? Perform test operation with 1. See, 16 is the even number I have taken. Once you perform AND operation with this, what it results in? All zeros, right? 0 ANDed with 1 will 0. Will be 0. So all bits will be zeros. If you get the result of AND operation as 0, we can infer that the input data what we have taken is an even number. If I had taken the value as 17, kindly see, if I had taken the value as 17, where LSB bit will be 1. If 17 is the input I have considered, then after performing AND operation with 1, what it results in? It's a non-zero value, right? See? So Z flag status will be 0. If it were to be odd number, Z flag status will be 1 if it were to be an even number. That's what we are doing here. Are you getting? So TST R0 comma hash 1 we have taken and we are performing AND operation. So if the Z flag status is 1, we can if it is 0, we can infer that it is see odd number. If it were to be 1, then we can infer that it is even number. This is another way of implementing the problem to check whether the given number is odd or even. Next, check whether the contents of R1 and R2 registers are same or different. So if they are same, then store 10H in R3, otherwise store 20H in R3. How to implement this problem? You need to compare the two numbers and test whether they are equal or not. What is the simple implementation? Yes?
TNK operation.
Using CMP.
Very good. You can use CMP instruction. Directly you can compare. If the numbers are same, when you perform subtraction, if I have taken two numbers as say 2 and 2, 2 minus 2 will result in 0. I can use CMP R1 comma R2 and I can check if they are equal. If the Z flag status is set to 1, I can infer that the numbers are equal. And if it is so, we will store 10H in R3, otherwise we will store 20H in R3. Otherwise, you can make use of TEQ instruction. So how to make use of TEQ instruction? TEQ, if the numbers are same, TEQ will internally perform exclusive OR operation, right? So
Yes, ma'am.
exclusive OR
Using
operation with the
except
same data it will result in what value? See, if I have
0.
taken as 0, right? 0, 0, 1, 0. If you have taken as data as 2, second number also if you have taken as taken it as 2, what it results in? We are performing exclusive OR operation. If the corresponding bits are same, means resultant bit will be 0. See, this is how I can make use of TEQ instruction to check whether the two numbers are equal or not. See, that's what we have used here. You can see move R1 comma hash 2, R2 comma hash 2. These are the inputs I have considered. and I've used TEQ instruction, TEQ R1, R2. Then we'll check if the Z flag status is 1, we can infer the numbers are same, otherwise numbers are different. This is how we can use TEQ. Performing exclusive OR with the same data will result in 0. One more method can be, I can go for reverse subtraction. If the numbers are same, let's say 2, 2 if I have taken, okay, I'll take the 2's complement of the number, second number, and I'll add it. I'll do reverse subtraction with 0. So you'll get minus 2. What will be the result? Minus 2 plus 2 will result in 0. If the numbers are same, if you take 2's complement of that number and if you add it, you'll get the same result. See, I've used RSB instruction. RSB R3, R2, has 0. 0 minus 2 will result in minus 2. I'll add as R3, R1. So what it result in? We are adding minus 2 plus 2. This results in 0. So then I'll check EQ R3. If the Z flag status is set, then we can infer that it is the numbers are same. Otherwise, the numbers are different. So if you are aware of all the instructions in ARM, you can come up with different solution to achieve the solution for this given problem. Hope this is clear. Have you all followed?